Welcome back. The previous video I introduced you waves. So in this video I will directly get into deriving or obtaining general wave equations. So for deriving this general wave equation, I will be considering a linear, homogeneous, isotropic and a source free medium. Such a medium is assumed just to reduce our mathematical competency, to make our derivation easier. It is nothing to do with the physical significance of wave equation. This wave equation can be derived for any independent space or medium. Okay, so for the purpose of understanding the wave, for the purpose of deriving wave equation, a more simpler mathematical way, we have just assumed this particular medium. Please keep this in your mind. So we will be, as I told in the previous video, we will be making use of Maxwell's equation in time varying field while trying to obtain the expression for general wave. So to start with, I will be considering the Maxwell's equation which is from Faraday's law. So Maxwell's equation from Faraday's law was curl of E equals partial differential of magnetic flux density with respect to time. So this is what we have as Maxwell's equation from Faraday's law, and this can be written or modified as curl of E is equal to minus mu d bar h by d bar t. This is because B vector is mu h. Now to proceed with, I am going to find curl, okay, on both sides of this equation. I am going to find curl on both sides of this equation. So it becomes curl of E on the LHS, and on the other side I will put this constant outside, and the other side becomes curl of partial differential of H with respect to time. Now on RHS I can interchange the operand, because this del operand is also partial differential and this deva by deva t is also partial differential. So I just interchange these operands so that my RHS can be written better in this form. So I just interchange this curl operand and this partial differential operand. So this becomes partial differential of curl of H, and LHS remains same. So the moment I see this curl of H, another Maxwell's equation comes to my mind. That is the Maxwell equation which was modified to satisfy Ampere circular law in time varying field. That is nothing but curl of H is J vector, that is conduction current density plus displacement current density. So this equation comes to my mind. And we have seen the relation between J vector and electric field, that is nothing but conductivity multiplied by electric field intensity is nothing but conduction current density. So I have sigma E and D is epsilon E. So substituting all that, this equation can be slightly modified like this. So I can have curl of H as sigma E plus epsilon partial differential of E with respect to t. So I will be using this, that is curl of H equal to sigma E plus epsilon d bar E by d bar t in this equation. I will be back substituting this so that my curl of E now becomes minus mu partial differential of sigma E plus epsilon d bar E by d bar t. I just substituted it. Okay. So now as you can see here, I have day bar by day bar t of E here and day bar t E of, so it becomes double, that is square. So I can write this equation in a better form like minus mu sigma partial differential of electric field intensity plus, okay, this minus comes inside, so I can write minus, okay, mu epsilon minus mu epsilon day bar square, because I have multiplied this day bar by day bar t inside, so this becomes day bar square by day bar t square of electric field intensity. So this is my curl of E. So curl of E is this. So let me mark this as some equation so that I can use this for later reference. Hoping that derivation is very clear till this point of time. I'll be using a vector identity now to proceed with. So there is a famous vector identity related to curl of, that is double curl of any vector. So curl of any vector. So in this case it is E vector for us. So curl of any vector is double divergence. Okay, that is divergence of that vector minus divergence square of that vector. So this is a famous vector identity which I will be making use to proceed with my derivation. So curl of any vector is equal to del dot that vector minus del square that vector. Okay, now see here, before directly substituting this into my reference equation 1, I am in which medium? I am in a linear, homogeneous, isotropic and source free medium. When I say source free medium, it is a charge free medium, right? So I will be making use of next Maxwell's equation here. So I will be revisiting another Maxwell equation, that is del dot D equals rho V. So this is another Maxwell's equation we have here, del dot D is equal to rho V, and in this particular medium del dot D becomes 0 because it is charge free or source free region which we are deriving this equation. So in a charge free region there cannot be any rho V. Rho V is nothing but volume charge density. So there should be charges to form rho V. So there are no charges in that medium. So rho V is obviously 0. So I get that del dot D is 0. So when del dot D is 0, this indicates you that del dot E is also 0, because del dot D equal to 0 is del dot epsilon E equal to 0. Epsilon cannot be 0, so it directly indicates that del dot E is also 0. So for this particular medium which we are considering, this in this vector identity, this del dot E term can be or should be 0. So that my vector identity simplifies as curl of E equals minus del square E. So this is my vector identity now. Now I will be using this and will be substituting it in. Okay, let me indicate this as second equation, but I can simply say put value 2 in value 1, value of equation number 2 in value of equation number 1. So I get my LHS changes like this now. So if I do that, I get the equation number 1 becomes del square E equals minus mu sigma day bar E by day bar T minus mu epsilon day bar square E by day bar T square. Now I have these minus signs throughout this equation, so I can rewrite this equation in a better form as del square E equals mu sigma day bar E by day bar T plus mu epsilon del bar square E by del bar T square. So this is nothing but wave equation. So we have the easily derived wave equation since we have help from Maxwell equation. We have already studied Maxwell equation for the interdependency of electric field and magnetic field. So using those Maxwell's equation, I could easily derive the wave equation. But as you can see here, this wave equation is applicable to electric field only, because this particular equation have electric field on left side and electric field on right side. That is, both RHS and LHS of this equation is directly showing you the significance of variation of electric field intensity, or basically variation of electric field. So that I call this equation as wave equation for electric field only. So this is wave equation for electric field. Yeah, now this indicates you that you should be able to derive wave equation for magnetic field also. But it is important to remember this equation. So I have del square E is equal to mu sigma del bar E by del bar T plus mu epsilon del bar square E by del bar T square. Okay, so before going to wave equation for magnetic field, it is nice practice to rewrite this equation in terms of D vector also. Okay, that is, if I multiply epsilon on both sides of this equation, I'll get epsilon E everywhere. That is nothing but a D vector. So if I multiply epsilon on both sides of this equation, I can get the same equation in terms of D vector. See, that is the beauty of this. Del square D vector mu sigma. So it is, the effect is just replacing E vector with D vector. That is nice, right? So mu sigma del bar square. Otherwise the whole equation remains the same. You just replace. But how I am replacing? Mathematically also it is possible, because if I multiply epsilon on both sides, I am going to get same equation. So I get two variants of wave equation for electric field. So both are basically representing same wave equation for electric field. Yeah, now it's time for us to check how to get a similar equation representing variation of magnetic field. So let me start with for deriving wave equation for magnetic field, I am going to consider the Maxwell equation curl of H equal to J plus JD. Okay, that is Ampere circular law. So I will directly write, now J is sigma E, we already discussed this, and this is epsilon del bar E by del bar T. So I will start from here for deriving magnetic field wave equation. Okay, so the procedure remains the same. I will take a curl on both sides. So this becomes double curl, that is curl of H, which is equal to sigma curl of E plus epsilon. So I will interchange the operand and directly write. So del bar by del bar T curl of E. So this we have discussed already. It is curl of this equation and you can interchange the operands. So I get this equation if you take curl on both sides. And the moment I see this curl of E, I know that I have another Maxwell equation, right? Another Maxwell's equation which relates this curl of E with del bar B by del bar T. Right? And this is nothing but minus mu del bar H by del bar T also. So I will directly substitute for curl of E, that is minus mu del bar H by del bar T, for curl of E here, for curl of E here. Okay, so that my double curl H becomes curl of H will be now sigma of minus mu del bar H by del bar T plus sigma deba by deba t of minus mu deba h by deba t. Okay, now let me rearrange the RHS and write it in a better way. So this becomes minus mu sigma deba h by deba t minus, because I have this minus sign, so minus mu epsilon deba square by deba t square h vector. So this is my double curve. So I'll mark this as the equation number if required. Okay, if required, I'll mark this as another equation. There I have used 1, 2, so I'll continue with equation number 3 here. So this is my equation number 3. So again, I'll be going with the procedure is very similar, pretty similar or pretty same. I'll be going with vector identity, the same vector identity. You know that double curl of any vector. So here my any vector will be h vector, because I need to know what is that. Okay, so this is true for any vector. So double curl of a vector is divergence of that vector minus del square that vector. I'll be using same vector identity, and here also we know that we have another Maxwell's equation. So it's better to highlight that also. See here, I'm using, so this is one Maxwell equation, I have used another Maxwell equation. Now I'm going to use another Maxwell equation, which is nothing but from the Gauss's law of magnetic field, that is del dot B equal to 0. So this is next Maxwell's equation which we are referring to. So we already know that del dot B is 0. So this directly indicates you that del dot H is also 0. Del dot H is going to be 0. So in this particular equation, this del dot H term has to be 0. Okay, this is true for the medium which we are considering for this derivation. Okay, so del dot B is 0. So my LHS is now just, or my curl of H is now just minus del square H. So this now I can substitute back into my third equation, right? LHS of my third equation I'll be replacing with minus del square H, so that I get minus del square H is equal to minus mu sigma deba H by deba T minus mu sigma deba square H by deba T square. And similar to the previous case, here I have negative signs throughout, so I can write this equation in a better way as del square H accounting for mu sigma deba H by deba T plus mu epsilon deba square H by deba T square. So undoubtedly this is the wave equation for magnetic field. So this makes my wave equation for magnetic field. Okay, so similar to the previous case, if I multiply mu on the both sides of this particular equation, the same equation can be written in terms of magnetic flux density. So this becomes del square B mu sigma deba B by deba T plus mu epsilon deba square B by deba T square. So these are the two variants of wave equation for magnetic field. So now we have the equations like del square E equal mu sigma deba E by deba T plus mu epsilon deba square E by deba T square in electric field, and if you replace E vector with H vector, you will get the wave equation for magnetic field. So it's very straightforward and very easy to remember the general wave equation in source free medium. You replace E with D, you get wave equation in terms of D. You replace E with H, you get wave equation in terms of H. You replace B with H, okay, or H with B, then you get in terms of magnetic flux density also. So you have now these 4 variants of this equation, but these are now treated as independent equations. Each equation will give you the variation of the wave independently in electric field and magnetic field. But since it has both the variations, that is del square E variation as well as del square H variation, I say that it is a general wave equation for electromagnetic wave. Okay, so for helping us to solve more problems, or it's always better to represent in general this 3-dimensional equation for all the vector fields. Okay, this 3-dimensional equation for all vector fields. So representing it in a general way, I can write that del square of all these vectors, that is E vector, D vector, H vector and B vector. So del square of all these vectors is nothing but mu sigma of partial differential with respect to time of E vector, same. Okay, so this E, D, H and B can be now treated as a column matrix. Okay, and you can find its variation, okay, plus you can find its variation with respect to these parameters, mu sigma of double partial differential of the same terms. This is nice. So this is how we generally represent E, D, H and B. So now we will get a more clear picture of this. Okay, so double variation, that is del square. Okay, double variation of these parameters is equal to mu sigma of the medium. Okay, mu sigma of the medium multiplied by time variation of these the same parameters added with mu epsilon of the medium into double differential of same parameters. So this will give you the idea of wave, how the wave travels in the medium. These are the equations which will give you that idea mathematically. So I hope the method of deriving general wave equation is crystal clear. That's all for this video. In the next video, I'll introduce you what is an uniform plane wave, and then we will try to derive uniform plane wave equation in free space. Till then, take care.